Hello and welcome to Tensar Ground Coffee. A few minutes on ground engineering to enjoy it while having your coffee. Well, here we are at the Tensar Technical Center in Blackburn, where we do all our testing. Now, you remember I showed you before the Bishop triaxial cell, one of the first triaxial machines to be built in the world. And do you remember what size the specimens were that went in there? The standard specimen size of about 38 millimeter diameter or 1.5 inches. But look at this we got here. This is also a triaxial machine, but the granddaddy of all the triaxial machines because it's 0.5 meter or 20 inches diameter and double the length. So look at the comparison between the two. So why is it that big? It's because of the particle sizes that we test. So we test up to about 50 millimeter particle size. So clearly a specimen that big is not large enough, is it? You get particle size effects. So there are rules of thumb saying things like the diameter should be about 10 times the particle size. So if we test something that's 50 millimeters big, particle size, we need to go to 500 millimeter diameter for the triaxial. Of course, when it's this big, we can't really place a big cell around the specimen to apply the confining stress, the cell pressure. So what we do is we apply a vacuum. And that's the noise you might be able to hear of the vacuum pump. We have a specimen here ready. So there are pipes going from the top cap out to a vacuum pump there. So that means we can get the confining stress up to about 80 kilopascals, which is plenty high enough for most of our applications, which are quite shallow. So we still have a rubber membrane around the specimen. So we have this rubber membrane you see here. The vacuum pressure is on, so you can see atmospheric pressure pushing in around the stone here. So we do some tests on various granular materials. And when we want to test one with a geogrid, we'll get a disc of the geogrid. There's an example there. And we'll put it at the mid-height. We may put more layers in, but generally we just put one at the mid-height there. So the whole idea of this is to test the material as a single composite. So rather than testing the soil on its own and testing the geogrid in air on its own and then putting the two together in an analysis model, we test them all together. So we are testing the mechanically stabilized soil. We are testing the effect of this geogrid on the aggregate inside here. So once we've set up the specimen, we do the test in the standard way. We apply a axial force here, a deviatoric stress. We measure the displacement. So we get the full mechanical behavior, the stiffness and the strength of the material. So we have done over 400 tests with this device on a whole range of aggregates, from sand to rail ballast to a whole range of graded materials used in road bases, for example. So we understand very well the mechanical behavior of aggregates stabilized by our products. And we put that information into finite element analyses, for example, of various applications. So we get a much better understanding of how our products perform in our applications. And that leads to new design methods, such as the T-value design method that we have for working platforms. That all comes from testing working platform materials, typical working platform materials in this device, putting the parameters into a finite element analysis, and then deriving the T-values to be used in routine design. Okay, I hope that's been an interesting overview of the granddaddy of triaxial tests. That's all for this episode of Tensar Ground Coffee. Thanks for watching and see you next time.